Hello. Okay. Um. So let's discuss the recent Div 4 round that has just finished. I'll just quickly set up my stuff um, before we start. But yeah. So I'm hoping I did solve all problems. This round was like one of the easiest rounds because problem G was really easy. Most people could solve it without even proving it. That's the idea. Um, but in general, I think this one is just one of the easiest different routes. I think F is the only one that's F and E are the only ones that really challenges people, and the others are just really elementary stuff. But yeah, let's start. The easiest one is A. I think everyone can do this. As long as you know your language, then you're fine. So basically, just take in the inputs, and then if this is true, then we can just add plus, or we can just print plus. Otherwise, if this is true, then we'll just print minus. And since the constraints give us that exactly one of these two equations is true, then you can just, I don't know, let's just implement it straightforwardly, just if and else. So it's just pretty straightforward. Just you know, um, if a plus b equals c, then just print plus, otherwise print minus, because exactly one of them will be true. Okay, so let's go for problem B. So what is problem B? Okay, so problem B is basically all of the even all of the even contained bag, or all bags that contain even candies will go to Mihai, while all of the odd or the bags with odd number of candies will go to Bianca. And Mihai can rearrange the array as much as he or she wants, and he or she wants to, or okay, he wants to uh, have strictly more candies at any point in time. And what I mean by that is basically Mihai and Bianca get candies in a row. So from the first bag to the nth bag. And Mihai has the power to rearrange that order. So this is very greedy in nature because Mihai has so much power. He can rearrange. That means that what if Mihai just ranges in such a way that all even numbers um, show up before all odd numbers. In some sense, the array would look something like this if we deal only with parity. And here, if it's 1, 2, 3, 4, it will become 2, 4, 1, 3. And in this sense, you have more chances of Mihai having strictly more candies, because from here on to the last E, it will always be greater than. Now we just have to check. We're now just interested in the segment containing only O's. And this will only be false if this will always be true if the sum of so how do we or just in some sense is like sum of events must be strictly greater than sum of odds. And that's the idea. That's the reason why this fails, is because if we do that greedy stuff, then as you can see, at this point in time, or actually at this point in time, 2 is not greater than the sum of odds, which is at this point 2. So the idea is just calculate the sum of the evens, and it should be greater than the sum of odds to output yes. Otherwise, output no. So this is just a simple implementation. Just add all numbers that are odd to the odd sum and all even numbers to the even sum, and do the decision problem in the end. And then let's go with problem C. So problem C is basically you have a string of only lowercase Latin characters, and in one operation you can change all um, you can choose a distinct English alphabet letter, and you can um, replace it with a 0 or a 1. And in one operation, if you choose one English letter, all of the other English letter with the same that are the same, that is the same with the one you pick, will be changed. So you want to make it an alternating bit stream. And how do we do that? Um, so our claim is that if, for example, if character A, consider its set of indices where it exists, let's say I1, I2, up to IK. If you change it to either 1 or 0, then this becomes, all of them becomes 1, or let's say 1. Then it only becomes a possible bit string if all of these indices have the same parity, right? So there's a possibility that it can be a bit string if all of these are even or if all of these are odd. Now we do this for each character, right? We do this for each character, and we do this for each character, and it should satisfy that, right? There's a possibility that they have the same stuff, and in that case, let us prove that we can construct a bit string. So that an alternate bit string if all of these things satisfy that all of their indices have the same parity. So what we can do is group all letters that have their indices at even. So let's say it will be like, so let's say it be letter 1, letter 2, up to some other letter, let's say letter N. And all odds will be grouped to letter, I don't know, N plus 1 up to letter 26. And we can now just turn these letters into 1, and we can now turn these letters into 0. And that's the construction for that. Or vice versa, if you want this to turn to 0 and this to turn to 1, it doesn't matter. So this proves that the condition that we just need to check is that all of the letters, their indices will be the same parity. So how do we code that? I think the easiest way is, or at least what I thought of during contest, is, or the most intuitive way is to create a variable, a 26 length array, a boolean array, initialize as false, and for each number uh, from each index 0 to n, we will uh, determine if a letter, right, a distinct letter appears to have an even index and an odd index. So in order for us to check that, if after the process of like check or after determining if or what are the types of indices a letter can have, can it have a even or can it have an odd, we can check it in the end that um, if both of the same time are true, meaning it has an odd index and has an even index, then the answer becomes no. Otherwise, the answer is defaulted to yes. Okay, so that's the first three problems, and I think almost everyone that has some background in programming has the chance to solve them um, that are not competitive programming. And now let's continue on with the harder problems. So for problem D, I think most people that are new to competitive programming get stumped with D based on the number of solves, um, or it's actually well distributed actually. So there's like 3,000, around 5,000, and then like around 3,000. But my friends that tried this contest got stumped with problem B. Okay, so what's this problem is basically you have some queries, and if it will ask you a question. If you turn all numbers from AL to AR to K, is the sum of the entire array odd? So a demonstration for that problem, let's pick this. So let's pick 2, 2, 1, 3, 2. And the first query is turn all numbers from index 2 to 3 to 3. So we pick, so this is 1, 2, 3, 4, 5. So these turn into 3. So the new array will be this. And now we check the sum of this array. So I think this is 13. And as you can see, 13 is odd. So this is correct. Or this is yes. So we output yes. And these queries are independent, meaning if you change this, it will just go back to the original array. So we'll just, so they don't affect each other, as is been explicitly explained in the problem statement. And now if we change to the elements with indexes 2 up to 3 to 4, it will be 2, 4, 4, 3, 2. And if we check their sum, this will I think be 15. And as you can see, it's still odd, so we print out yes. Where's the case where it fails? It fails at fourth query. So 1 to 4, it becomes 9. So it becomes 9. And this will be 38, and which is even. So it will be no. So how do we solve this problem efficiently? Obviously, you can just brute force it and turn everything into whatever number, and then we can like just add them and then check their parity. But given the constraints, it's quite hard to do that, and in fact, it will not pass the time limit. And it will take a very long time for it to process. So it will be like O of n squared if I'm not, or O of n cubed, which is an order of 4 times 10 to the 5, or 4 times 10 to the 10, which is really, 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 really slow. So how to so the intended solution will be just O of n. So how do we solve this problem in O of n, or O of n, or O of n plus q? So if you notice, like let's say we have this array of numbers, and if you check or if you choose two, or if you consider the segment LR, if you turn all of them to K, what happens to the sum? How does it change? Like given that your sum is S, what happens? Um, so S now becomes S minus the sum from L to R plus K times the length of the segment, because there are that amount of Ks, which is R minus L plus 1. So this becomes the new sum. And now we can just check whether this is even or odd, and that's it. And since it's independent, we don't have to update anything. So we just check this if this is even or odd. But the problem is that we know how to get this. This is pretty easy. We also know this. This is just a sum of the whole array. But the problem is this. Yeah, how do we get this sum? And in competitive programming, there's multiple ways to do subqueries. But the easiest way to solve this is using prefix sums, because it's static. Nothing's getting updated, as I've mentioned before. And even if you do update it, it's like, yeah, nothing's getting updated. So you don't have to do like maybe like segment trees or sparse tables. Actually, sparse tables are not. I'm sorry, that's not. I don't think that's not an online algorithm. For example, segment trees or fenwick trees or any other RMQ or like LCA or whatever. You don't have to do that. You just have to do prefix sums. And what I mean is that sum of a segment can be computed as follows. So let pi be the partial sum from a1 up to ai. Okay, and how do we compute? If we pre-compute this, and this can be pre-computed in O of n, basically just use the previous sum and then just append AI. So what I mean by that is pi plus 1 is basically just pi plus AI plus 1, right? So you can pre-compute this in O of n. And how do you get the sum from L to R? This is just P of R minus P of L minus 1 if L is greater than or equal to 1. Otherwise, it will just be PR, right? Or in fact, it's just A sub 1. Or this is strictly if we're using one indexed. So it can be computed fast, and that's it. Now we know how to get this up. There are other ways that are easier, or like in the sense that you don't have to know what prefix sums are, I guess. Actually, there's other ways. What we can do is like compute the prefix sum here and compute the suffix sum here. And then just add k times r minus l plus 1. And then check that. That's another way. But I think during contest, this came up to me. For some reason, this was the first idea that came to mind. But you can also do that. And you can also, I think you can also just care about not necessarily the sum itself, but the parity of each prefix and suffix. I think that's easier. But you don't really have to, I don't know, to think about that. Because it might be like, I don't know, it might save some more space if you use booleans, right? You know only the parity. But during contest, this was coming from being experienced contestant myself for like about a year. This was more like intuitive and fast to do. But it didn't really came here in this contest for doing things fast. I don't know, just solve the problems. Maybe I can learn something. And apparently I didn't, because I knew all the problems. But in any case, yeah. So let's start with problem E. Oh, I forgot how to implement problem D. Problem D is again just using prefix sums, right? And then just calculate the sum and then do what I said earlier. Check whether sum minus the sum of the subarray plus the length of the segment times k is odd or even, and that's pretty much it. So problem E, okay, so this is, I think, the first interactive problem in a Div 4 round that I've encountered, and let's discuss. So the problem basically means that you are given the number of pebbles per each for each pile, or you're given the number of stones per each pile, and strictly one of the stones have weight of 2 and the rest are ones. So meaning the weight of a pile that does not contain the special stone is literally just the number of stones. But now, as you can see here, the number of stones is 2, but since this is weight 2, then it's much greater. So this one's the pile that contains the special stone, and you want to find the pile that contains the special stone. So how do we do that? And in one operation, you can ask the person, or whatever, the director. You can ask, what is the sum of the weights given k indices, or given k piles. So for example, you ask what is the sum of pile 1, 2, and 4. That will just be 1 plus 2 plus 1, that is 4 plus 4, that will be 8. And that's the only thing that you can do, and from that you need to use at most 30 queries to ask the director and determine where the pile contains the special stone, or what pile contains the special stone. And this is a very standard problem usually taught in universities, or if not, you will encounter this in your first lessons in competitive programming, or in general just algorithms course, is binary search. And so binary search, the idea is, this is in general, binary search is used for like monotonically increasing values, or like not monotonically increasing, but like value special functions that has properties, maybe associative functions, idempotent functions, and so on and so forth. But in general, this is a fast process that like uh, it repeatedly um, halves some array and decide if it's in left or right, stuff like that. So how do we answer how do we answer this problem? So given these piles, like for example, we have 6 piles, right? Let's half the pile. Like let's consider this and this. So what we can do is we can ask if this set of numbers is the sum greater than the number of piles, or not the sum, but what I mean is the weight. So if this is true, then we already know that the special stone is somewhere here. Why is it not here? Is because at up to this point it's already greater than the number of piles, so it's one of these piles. So it's ultimately not here because this didn't contribute to the answer. um, Otherwise, if it's not here, then it must be here, right? It must be here. Then the special stone is right here. So the essence of binary search comes to play. we can just half the array, and then we from there we can like ask, is this sum what's the sum of this, and we can also compute the number of piles in this or the number of stones in these piles. Actually, not number of piles, but the number of stones. Sorry, we compare the number of stones to the weight. So if this is true, then the uh, special stone is here. So we can recurse to this array and only consider this. So we discard this array. And similarly, if now we consider if that's not true, then we just go here and recurse in this array. Yeah. Um. Hmm. Yeah. So that's the basic principle. We can implement the sum of the number of stones using again prefix sum from previously, and we can like keep on doing that. And yeah, let's determine how we implemented this at all. Also, for some reason, I computed the suffix sum, which again doesn't matter. But yeah. So we don't actually need a suffix sum. I don't know why we pre-computed the suffix sum. So again, all we need to know is the sum of the left array. And it turns out that we can do some optimizations. We actually don't need to just get this, but we can also just access to this. For example, we recurse in this array. We can just ask this sum, because from what we concluded earlier, if the special stone is here in this half, then this has this weight. The number of stones here is equal to the total weight, which means that if ever we compute this prefix sum here and it's greater, then it must exist in this half of the right array, right subarray. Because we can like prove that by like considering the difference of the weight in stones, and this contributes 0 to the difference, something like that. And so we only really care about the prefix sum um, to avoid thinking too much about the algorithm. So how do we implement this problem? Basically just pre-compute the prefix sums, as I've said earlier, and um, pretty much uh, do binary search, where you start from the first index up to the last index, and you have to iterate or keep iterating while the left pointer is less than the right pointer. This is just some implementation details that I've tested out, and I'll explain why that is the case. But yeah, compute the middle element or the middle index, and ask what is the sum up to that index, and that will just be the prefix sum. Well, actually, it turns out that it turns out that you can just sum them up. You don't actually have to compute the prefix sum. So since you print it, you can just like take the sum anyways. So yeah, that's one other minor detail that you can have, and it's still um, of log n. Or I forgot to mention that binary search is time complexity is in this case will be O of n log n, because we're considering the sum for each. It's because we're printing everything we're printing the index up to that index. So this will be still of n log n, and we get the sum, or we get the weight. And if this is the case, if the or if the weight is greater than the stones, then r becomes m, meaning up to the mth point it will still be included as um, possible choices for that possible choice as a pile that contains the special stone. Otherwise, it will be L plus 1. So these the subarray doesn't matter anymore, and we just move into the other subarray, and we don't care about the middle index that we computed earlier. We just go to the next of it. And that's precisely the reason why we set this condition to L minus R, or L is less than R, is because is because uh, is because R and M can be equal at any point, or at some point, right? So R and M can be equal at some point. And if we update, uh, L can be updated to M plus 1. If I recall correctly, yeah. Actually, yeah, that's the trick. I don't know why this implementation detail is that. I haven't like, proved it yet, but for some reason it works on the test, or the sample test cases, and it works for the test cases. But um, for some reason when I tried equals, it didn't work, and I can't prove the details of that. But yeah, just print r plus 1 in the end. Or maybe that's the case because what we're trying to print is r, the right pointer. So maybe that's the reason. I don't know. I completely don't know. But let's go to the next problem, which is in this problem set is kind of the hardest in some sense because it's implementy. Problem G is like you can get problem G by literally just guessing the solution, and based from the number of solves you can see, oh wait, it must be easy, so maybe I can guess the solution. But that's not the GigaShad way of approaching problem solving, and you have to prove it. And during contest, you should prove it if you're GigaChad, or at least convince yourself. So in problem F, basically the ball moves diagonally, and if it hits the wall, it will bounce or it will reflect. So if the direction is down left, it becomes upright, or wait, down left, it becomes up left. If this is the direction of the bounce, if it bounces in the corner, it completely goes to the opposite direction. So one thing to observe with problem F is if we, okay, let's just go to another scratch. If we consider a cell, right? We consider a cell. Notice that there are only 4 directions where it can come from and it can go out from. Okay. The idea is that suppose the first time it enters is here, and then so it exists here, and then maybe it enters here, so it exits there or something, and then maybe it for some reason it enters here, and then it enters here, so it will go out here and it will go out here. As you can see, if ever it enters the cell again, here, or here, then it must repeat the path. Okay? It must repeat the path because it takes the same direction as before. So if it enters here, it will go there again, and it must take the same path as before. So that's the general idea. So if we have visited all directions from this of this cell, if it's a middle cell, then we're fine. However, there are some edge cases that we should consider. For example, in a 5 by 5 or in an odd by odd um, matrix or an odd by odd room, we can have this case where we're only really visiting um, two directions. So the thing is, we don't have to consider the directions. All we have to consider is the number of times you visited that cell. And in which case, what we can do is count the number of times the ball visits a cell. And notice that if it visits a cell greater than or equal to 4, actually let's increase that and let's be greedy in our implementation. Let's increase that to 5. Notice that there's no point of visiting that cell already if we have already visited 5 times. Or let's say just 4 times because it makes more sense. Right? There's no point because we have already visited all directions to come from. So it must repeat the path after that. So it doesn't make sense to repeat that path anymore. And we already know that path before. You can increase this if you're not sure, but I think it's 4. But you can increase this stuff. And since it's just a factor 4, then you can implement this process in 4 of O of 4 and n, which is just n by m because 4 is extremely low. And that works in, or not n by m, or yeah, n by m, because it works because n by m is just 5 times 10 to the 4. Then how do we what are the decisions to consider? Well, if we visit I2 J2, then obviously the answer is yes. And otherwise, if we stop already without visiting I1, I2 and J2, then the answer is no. And we print -1. So that's the idea of problem F, and the hard part about problem F is not necessarily that idea, but how to implement it, because I implemented with so many decisions. So how did I go about this? I counted the number of times you visit a cell, and you start from I1 and J1. So let's just do while true. So if I equals I2 and J equals J2, I just did -1 because I implemented the visited array in 0 indexed. The answer is true, and now we can break out of the loop. Otherwise, you visit the cell and check if it has already been visited at least 4 times. If it was visited at least 4 times, then you know that actually it should be 5 times in this case because I did this first. If you already visited it 5 times, that means that you already went through all directions and there's no point of continuing the path because it's just gonna repeat. Yeah, and we know that this loop will always terminate either this or this because of the fact that there are only finite cells and finite directions for each cell. So at some point it will either visit a cell 4 times without visiting every cell, or it will visit every cell, right? Until we get to a point where we visit a cell 4 times, and this loop will always terminate. And now we just have to implement our direction shifts. So for each direction, let's, without loss of generality, the direction is dr. If we are at a corner, we just reverse the direction, and since we're counting the number of bounces and we're going to print that, we'll increment the number of bounces. And otherwise, We can actually implement this in a way like maybe this I equals n minus 1 or j equals n minus 1, then we increase the counter, and then decrease this by 3 lines or something. But actually, it's the same thing. It's just 3 lines as well. But anyways, yeah, that's one way you can do that process to reverse the direction. And if it's down right, okay, going down right, so down right, and it hits the last row, then it must go here. That's why it becomes upright. So that. And if it hits the last column, so down right is like this, it must go down left. So it goes down left. And those two previous directions that I mentioned, or previous conditions that I mentioned, are conditions where the ball needs to bounce, so increment the counter variable. Otherwise, if it doesn't hit anything, then it just continues to that direction. So just shift or just move the ball. So it becomes, new coordinate becomes I plus 1 and j plus 1. And do the same trick for all of the directions. You just have to be careful with your directions and your increments and decrements. And if we have found the answer, we print the number of bounces, and otherwise we print out -1. And I kind of understand why only 900 people were able to solve problem F, is because they might have not thought of the visiting 4 times idea. And they might have thought that this path can go infinite, or like can go very random, that it becomes very infinite and unpredictable, that it doesn't terminate. But in fact, it will cycle at some point. Because again, there are only 4 directions. And you only have 4 operations, and it's not random. And now the last problem is problem G. So I'm pretty sure almost most of the solves in G2 didn't care about G1 for some reason. So this is actually a kind of a standard knowledge. I don't kind of remember where I first encountered this problem. But the idea is that you're given an array A containing the number 1. And in one operation, you can get a subsequence of that array and sum them all up. Right? You sum them all up and then append that to the new array. So you're basically producing a new number from the previous numbers that you have done, and using that sum of a subsequence. And you have a final array C, and determine if you can obtain C using the operations and initial array A. So let's demonstrate that fact using a sample test case. Let's choose this test case. Which one should we choose? Let's choose this test case. So what I can do is, like, we have 1 here, right? Obviously, there's only one way to progress after 1, and that's choosing that. And there are 3 1s. So what I can do is I can take another 1 and then just have 3 1s, and then I can sum 2 1s, and now it becomes 1 1 1 2 2, or 2, sorry, just 2. And the next is 4, and now the next array will be 1 1 2 4. And notice that we can generate 4 because we can have 1 plus 1 plus 1, or 1 plus 1 plus 2. We can generate 2 because we can have 1 plus 1, and we can generate 1 because we can have 1, we can generate 1 because we have 1. So that's the idea. And you might soon realize that, oh, that an important factor is that we only really consider the sorted version of array C. Why is that? If we swap, um, so let's see, let's do this. If we swap two numbers and say, okay, you generate 4 first, um, like let's say somehow you are able to do that. If you generate 4 from that, it might be that this lower number can be generated before this because because the only number that you have added before is the number that is greater than this, which means that it will never be used as an addend to generate this number. So we're basically just considering this. So we can literally just swap them. And we can do that until all of the elements are sorted in non-decreasing order. And now what happens? So my claim is if, say, the partial sum from I minus 1, or from 1 to I minus 1, is greater than or equal to the current number AI for all I in the sorted, or no, this should be C, in the sorted array C, then we can form it. Otherwise, no. So we can prove this. So this is my claim. We can prove this by induction. So suppose for the array C1 up to C I minus 1 that you can form any form any sum from 1 to pi minus 1. So we assume that this is the case. We have to prove for the case for C1 up to Ci. And how do we prove that? So there are two conditions if pi minus 1 is greater than or equal to Ci, or pi minus 1 is less than Ci. So Ci is greater. So in this case, it's obvious that you cannot never form this case because the maximum sum that you can take is just pi minus 1, which is less than the current element. So it's impossible. So it must hold that pi minus 1 is greater than or equal to Ci minus 1. So this is a condition that we are able to assume. If this is the case, then we can form, since we can form 1 to pi minus 1, we can form Ci plus 1, Ci plus 2, up to Ci plus pi minus 1, which is pi. And since Ci is less than or equal to pi minus 1, then Ci plus 1 is less than or equal to pi minus 1 plus 1. Or wait. Yeah. Okay. So that means that so this is less than or equal to. So if it is equal to, then this is from pi minus 1 plus 1. So the equality case up to pi. And this means that we can form 1 to pi minus 1 up to pi, which means that we can form 1 to pi, and that proves it. But if it's less than, then that means that this sum has already been, you can already get this sum. So there exists Ci plus k that you can already, for k from 1 to pi minus 1, that you can already form using these the previous set of numbers. So that means that again it overlaps. So for example, Ci plus 1 is here in the number line, Ci plus 2 is here, and so on. Ci plus pi minus 1, and let's say pi minus 1 is here, right? And pi minus 1 minus 1 up to 1. So it overlaps, meaning that we can form any number from 1 to pi. And that proves our induction. So the important condition that we only really need to check is this case. And how do we implement that? Well, first we sort C, and obviously if C0 is greater than 1, then um, we can never have this case, right? Initially A contains 1. So the minimum of C must be 1, because all of the numbers are positive integers, or not this. And you can only generate really positive integers greater than or equal to 1. And then we can initialize our sum, and if ci is less than or equal to sum, we can just update our sum and continue. Otherwise, our answer is no. And that's pretty much G. Why that explains why G was solved by 6,500 people. And more solves than E and F. And I don't know what's an intended solution for G1. But yeah, I think DP can be, you can solve G1 using DP. And how to do that, because notice that CI is at most 5,000 and this is 5,000, so we can like do all of n squared. We can like check whether each number from 1 to 5,000 can be, or for each iteration we can check whether we can form this sum and so on and so forth. Using the previous numbers. And I think that's the general sense of this, the intended solution for G1. And I think even G1's intended solution is harder than G2's intended solution. So people are naturally just going to go straight for G2. So I didn't try to think about how G1 was intentionally solved, because G2 was the harder version and for some reason is easier to implement. But in any case, that's it. You just have to prove G2. So in summary, this div4 round was actually one of the easiest div4 rounds. In fact, as a proof, because I AK'd it. And I think the last div4 round I AK'd was the first div4 round that I AK'd. And it's, I think, harder than these problems. So yeah, this one's a good welcome for beginners, and also a good review for experts. And thank you for watching. I hope you learned something here, and if you're an expert, I hope you fulfilled what you came here for. Thank you guys.